80, that was a tough one last night. We were keeping tabs. Let's go back to 3.1. Let's do another. It's been a long weekend, and I was gone yesterday. So let's look at an absolute extremum problem, right? And this is when we haven't looked at one exactly like this anyway. And those assignments are open now, right? Okay, good. So I want to go through an example where we use that table method again. I want you to really get used to using the tables. From the next 3 or 4 weeks, well, 3 weeks probably, we're going to use tables a lot. We'll keep building on them and we'll keep adding parts of the tables. Eventually we'll be able to add all kinds of things, like we'll be able to use the tables to represent asymptotes, horizontal and vertical asymptotes. There'll be a ton of stuff that will end up being wrapped up in these tables. They're pretty sparse right now. You probably are wondering what's the big deal about these tables. But with time, you'll see that they get better and better. There's more and more stuff being added to them. Okay, questions? No? Okay. So if we want to find absolute extrema on a closed interval, let's just quick review. Where are the only places that absolute extrema on a closed interval could exist? Critical numbers, so the interior critical numbers, right, between the endpoints or endpoints. All right, so we got the endpoints, we got to find our critical numbers. All right, so review of critical numbers. There are two kinds of critical numbers. They both have to do with the derivative. Where it equals 0 is one part, one type, or it's undefined. Okay, so we need a derivative. How do we want to rewrite this function? So x to the 1/3. So what is g prime of x then?
X to the negative 2/3.
Okay, so I'm just going to write that as 1 over 3x to the 2/3. Everybody agree? Okay, I want to write it that way because it's useful for us to have, if there are denominators, it's useful for us to have denominators, because the other thing I'll just briefly review, when we write functions in a rational form, it's easy for us to find the critical numbers. Where do we look for the zeros of a function if it's in rational form? What part is equal to 0? The numerator. Okay, so the numerator is equal to 0 to find the zeros. Where is a derivative undefined? The denominator is equal to 0. Okay, good. So in this case, are there any places where this function is going to equal 0? No, there aren't, right? So we know that we're going to get no critical numbers where the derivative is 0. But where is it undefined? At 0. Okay, so we know that g prime is undefined at x equals 0. So now we can make our table, and we can use our table to just quickly compare endpoints and critical numbers, the values of the function, to find the absolute extreme. Right? So we get our first row, values of x, and just think of that as the x-axis. And then we get g and g prime, and we only need those 3 rows for now. Okay, so our interval goes from -1 to 1, and so we're going to represent it exactly that way. So we get closed brackets, -1, +1. We can plug in the values of the function at -1 and 1 right now. What are the values of g? What is g at -1? What's the cube root of -1? -1. What's the cube root of +1? 1. And then we get this interior critical number at 0. And to remind us that that's a critical number, we know that the derivative is undefined there, so that tags it as a critical number, doesn't it? Because we get one of those key things, one of those 2 things happening to the derivative that we look for with the critical number. And what is the value of the function at 0? Well, it's 0. It's undefined. The value of the derivative. What's the value of the function at 0? Sorry, 0. Okay. So what's our absolute maximum? 1, 1. The absolute maximum is 1, and it occurs at x equals 1, right? What's our absolute minimum? -1, and that occurs at -1. Okay. Remember, we can look at these. These are sort of like slanted, or they're tipped up and down versus sideways. So just think of those as ordered pairs. Right? Okay, so just to summarize, we got x equals 1, absolute minimum of -1 at x equals -1, which is represented by that point. Okay? All right. So I think we got the hang of that stuff. Questions on that?
No, will you just scroll up to
Sure.
the second slide? We won't
Sure.
sure.
How about right
Oh,
there?
it's on.
Right there?
Yep.
Does it help if I move it around a little bit? Like that
Yes,
picture?
I already got the picture.
Okay. All right, so now we're going to look at existence theorems, right? And we've already seen this a little bit, but now we get into, like, we use these more often. So what are existence theorems in calculus? Existence theorems, I think I've already talked about this briefly, but we're going to look at another one. Two parts to an existence theorem. There are some criteria that we have to meet, and if we meet those criteria in the theorem, all the theorem really does is then it guarantees the existence of something. That's it. It doesn't really help us in that it gives us a value, or it doesn't really tell us anything absolutely profound about it we can apply directly to an individual problem. It just tells us if it's worth looking for something. If we meet these criteria, then it guarantees that it's there. Then we can go find it using calculus and algebra. So the one we're going to look at today is, there are two of them. And Raleigh's theorem is really, it's kind of a sort of a non-starter. We don't really ever use Raleigh's theorem, and you'll see why in a little bit. There's a more general version of this that we're going to use called the mean value theorem that just replaces this. But it's worth just considering Raleigh's theorem, because then we can go one step further with the mean value theorem, and it's kind of a step process, right? So let's look at this. Now here's Raleigh's theorem. What are the criteria? So that's the if part. We're always filling in the blanks. If this is true, then the theorem guarantees the existence of something else. It's like an if-then. So what's the if part of this? Okay, the function is continuous on a closed interval, right? From A to B. Okay, what's that mean? Let's pause there. What's our working definition in terms of me writing on the board or you writing on your notebook? What's that mean? Yeah, pen never leaves paper from A to B, right? Okay, what's the other part of that? So that's, say it again. Okay, differentiable on the interior interval between the endpoints. Now this is one I want to make sure we get this, because this is a word that we throw out a lot in calculus. But what's that mean to be differentiable? And let's get the terminology straight, because like a lot of times, and that doesn't bother me, but you want to make sure you get the terminology right. What's the noun and what's the verb when we're talking about the process of taking derivatives, which is what everything we've done so far this year is revolved around taking derivatives. So the verb is to differentiate, right? To differentiate means to take the derivative of, right? So if a function is differentiable, then that's an adjective, I guess, right, that describes a function for which we can differentiate, right? We can take the derivative, right? So if it's differentiable on the open interval from A to B, it means that I am able to take a derivative. The derivative exists, right, every place on that interval, the interior interval, okay? Does that make sense? Okay? So it is literally like it's take the derivative on that interval. What does that imply then? If I can take the derivative, if the derivative is defined everywhere, that should tell us something. We've got to peer a little more deeply. Think about what a derivative is and what it represents. And it represents a slope. But let's think about the kinds of places where derivatives don't exist. This is telling us that it does. The derivative does exist from A to B. Where are some places where it doesn't exist?
It doesn't exist at sharp points.
At sharp corners, right? That's important. So if it's telling us that this function is differentiable, between the endpoints, and it's continuous, which means I can draw the function without picking my pen off the board, combined, those tell us something really important. Our textbook doesn't use this terminology, but every professor I had in college and in grad school always did. So this is what I'm going to show you. We call this smoothness. If you combine those two things, those two criteria in math, we can combine into the single criterion. We just say that the function is smooth on the closed interval, right? And smooth is descriptive here, right? Smooth means that if I'm graphing this thing, I could draw my hand along the function. I'm never going to cut my hand on a sharp corner on the function. right? It's always gonna be nice and smooth, okay? There's no jagged cusps on the function, okay? So if it's continuous and differentiable, then that's true, okay? Keep going. So the criteria, if it's smooth, if it's continuous and differentiable, there's one other one up here though too. What's that? F of A equals F of B, right? Think what that means. The y coordinate at x equals A equals the y coordinate at x equals B, right? Okay, let's put all that stuff together in a picture, right? If I were to draw a picture of this thing. So we've got this interval going from A to B. I can graph the function without picking my pen off the board. It's smooth, right? There's no sharp corners on it to scrape myself or cut myself on the function. And we know that the value of f of A, whatever that is the same as the value of f of B, right? They have the same y coordinates. You fill in the blanks. What's probably going to be the outcome of this? What's that going to guarantee that we're going to have? Not necessarily. It could be sinusoidal, it could be cubic, but there's something that's got to happen there. If the function is smooth, so there's no sharp corners, but it's continuous, and I'm going to start at the same y value that I end up, something significant has to happen between those endpoints, guaranteed. Okay, I'm going to get some local extreme or relative extreme, aren't I? I'm going to get and even without even specifying the extrema part of it, we could just say there's going to be some places where the function has to have a zero derivative, right? Some horizontal tangents. Everybody agree? Okay, so there's no way that I could avoid having at least one of these places where I'm going to get a point of tangency where f prime of, we'll call that C1, f prime of C1 equals 0. Now there might be multiple places. In this case there were. There's another place right there. We could call that C2, right? In this case there were more than one places, but there has to be at least one. That's what the existence theorem tells us, is that on this interval, on this interval, there's going to be at least one number C between A and B such that f prime of C equals 0. Could be multiple, right? What good does that do us? Well, I mean, now we know that we can go find them without wasting our time, essentially, right? Okay, so that's Raleigh's theorem. Okay, the mean value theorem is not as restrictive. The mean value theorem, notice that we remove a criterion. Well, I guess there's criteria, but if we combine these as one, we could even say there's only one criterion. So now all we're going to say is, if we know that we're going to get a function that's smooth on the interval from A to B, then you tell me what has to happen in between this time. And I'll give you a hint. The mean value theorem is just like tilting Raleigh's theorem. Now think about that. So we're going from A to B. So this time it doesn't guarantee that f of A is equal to f of B. So I could have a point right here, for example, with coordinates A, f of A, and I could have a point up here that's at a different place, right? That's at B, f of B. But if the function's smooth, if I can draw it without any sharp corners between those endpoints, something else significant has to happen. Well, I mean, no, there don't have to be relative extrema this time. I'll prove it to you. Here's an example of one that doesn't have any relative extrema, right? So I don't have to have relative extrema. I might have relative extrema. Let's say I do. Say I do something like that. But there is something else important between those endpoints that has to happen. You know, that's significant to us. What do you think?
There is going to be a point along that line that we just went straight in between the points where derivative is going to be the same slope as that line.
Okay, that's it, right? So the slope of the secant line, what's a secant line in math? Right, a secant line is just a line that connects a function in two distinct places. So presumably this function, maybe this function is defined outside of our closed interval, but we're only interested between the endpoints A and B, right? So if we connect those with a secant line, okay, a secant line is a line that connects the function in two places. Well, the slope of the secant line represents an average rate of change, right?
Yes.
Okay? So let me summarize that. So. Right? Slope of the secant line. What is that in terms of my endpoints? What is this is just algebra 1 stuff. Slope is equal to rise over run, right? So what's my rise? If I'm going from this point to this point, I'm rising by f of b minus f of a, right? Okay, and I'm running by b minus a, right? So the slope of the secant line f of b minus f of a over b minus a. Okay? There's my difference quotient. Remember, that's what we call that, the difference quotient. Okay, well, there has to be at least one place on the interval where the slope of, not a secant line, but the slope of what? The tangent line is equal to the slope of the secant line, right? Where is it going to be visually? Well, visually, I mean, it looks like it's about right there-ish, right? That looks like that's about the spot where the tangent is parallel to the secant. That's what it looks like on our graph. But what the mean value theorem guarantees us is that somewhere in there, there's going to be at least one place where that, it might be multiple places, but there's going to be at least one place where that happens. Like if I drew this curve, for example, here's an example of one where there are two. There's going to be one there and one there, right? There's going to be at least one place on the open interval where that's the case, if it's a smooth function, okay? Do you see what I mean by saying that's just Raleigh's theorem tilted on its side? Kind of tilted a little bit, right? So now we're taking these endpoints and we're just doing that to them, right? And what used to be, the slope of the secant line used to be 0. Now it's no longer 0. Now it's something else, right? It's this. That, isn't it? Right? Okay, so that's all it's telling us. There's going to exist some place where this happens. Okay, so let's try a couple problems where we apply this then. So in each of these cases, in math, we just MBT in calculus, that's just mean value theorem, right? That's when you see MBT in a calculus class, that's what you're thinking, mean value theorem. So if it applies, find the values of C that are guaranteed, right? So we'll look at 3 examples of this. Here's our function, f of x, here's our interval. So a is -1, b is +1. So let's first ask ourselves, does it meet the criteria? It's just 2 things. Is it continuous and differentiable on that interval? Well, is there any place where this function is discontinuous on that interval? No, no x's on the bottom, right? We're good. So we meet that criteria. Is it differentiable? Yeah, it is. And we could demonstrate that pretty easily. If I were just to distribute the x, I'm just going to get a polynomial, right? So we'd rewrite f of x is just going to be x cubed minus x squared minus 2x. Yeah, that's obviously differentiable. If I take the derivative, I'm just going to get another simpler polynomial. We've seen that trend. So let's take the derivative. What do we get? It's an easy one. What is that? 3x squared minus 2. Okay. So there's our derivative. So how do we know that it's differentiable? Right? It's take the derivative of both. Well, we just did, didn't we? Right? Are there any places where the derivative doesn't work? Because I want to point out something that there's a really important relationship there. If I look at that derivative, think about the process your mind's going through. You're searching for places where the derivative doesn't exist, or excuse me, where I can't take the derivative. Like, what would be the kinds of places where you'd say, okay, no, Mr. Ray, there's gonna, like at x equals 2, it wouldn't work? What would have had to have probably happened at x equals 2?
Divide by 0.
Maybe I divided by 0, right? Okay, so here's what I want to impress on you then. When you're looking for a region of differentiability on a function, you're doing the same thing that you did when you looked for the continuity of the original function, you're doing to the derivative function. You get that relationship? So when you look for differentiability, all you're really doing is searching for continuity of the derivative function, right? Okay, so backing up to these criteria, this is just doing what you did in the yellow step to the derivative. That's it, to the derivative function, okay? So would you agree that this meets the criteria? So now all we have to do is, we've already found the derivative, so it's just an algebra equation. Right now we want to figure out where is the derivative equal to the slope of the secant line, right? Well, the slope of the secant line is just going to be, it's that difference quotient. A is -1, B is +1. Here's our function, right? So that's just going to equal, in general, f of 1 minus f of -1, right? Divided by 1 minus -1. But we can be specific. What is f of 1? -1, is that right? -2, isn't it? -2. Minus, what's f of -1?
Oh, yeah.
I'm going to get -1 minus 1 plus 2, is that right?
Wouldn't it be plus 1 because that's negative?
Wait, it's 1 minus?
Wouldn't it be -1 plus 1 plus 2?
Well, no.
Squared.
It's
Oh,
not,
squared.
because it's squared, right? So I'm going to get a -1 minus a 1 is -2 plus 2, right?
Yeah,
So it's 0, okay? So -2 minus 0, 1 minus -1 is 2. So that's just all equal to -1, right? So we just want to answer the question then, when is my derivative function equal to -1, right? Everybody agree? Okay, by applying we're looking for the places where the slope of the tangent line, derivative, equals the slope of the secant line, difference quotient. And now it's just algebra 2 stuff, right? Or even, maybe it's even algebra 1 stuff. We're just going to solve this quadratic equation, so let's review that. How do we, you walk me through it, not really review it. How do we solve this quadratic equation? What do we got to do first?
You accidentally use 1 as derivative instead of using the f of x, and then you end up with -1, and then you use that here instead.
What do we do?
You made a mistake.
I did? What did I do?
No, I made a mistake, and then that mistake solved the next one.
Oh, I got you. Okay, what should you do?
Not make that mistake.
Not make that mistake. But if I'm going to solve any equation, I'm just going to put it in standard form, right? Add 1 to both sides. So we're going to get 3x squared minus 2x minus 1 equals 0, right? And now you got all your options available. Quadratic formula would always work. Here's one where, once again, we can use our little trick. If it's going to factor, it's going to factor pretty easily. There's only one way we can multiply and get 3 and 1, right? How many ways can we multiply and get -1? Either -1 times 1 or 1 times -1, right? So the only ways that this could factor conveniently would either be, we're either going to get a +1 and a -1, or a -1 and a +1. Just see which one gives you the right cross product, right? So what happens if let's take the top one. Was that going to work? When I distribute the 3x, I'm going to get my 3x squared, of course. We know we got to get that. We know we're going to end up getting +1 times -1 is -1, but which one's going to work in the middle? 3x distributed here is going to give me a -3x. If I distribute the 1, I'm going to get a 1x. That works, doesn't it? Would you agree? I get my minus 2x. If I pick this one, I'd get +3x and -x. I'd get a +2x. So that one doesn't work. And it does factor, right? So we end up with 3x plus 1 times x minus 1 equals 0. What are my solutions? Because there's one more important step here that we got to make sure we don't lose out on. Okay, good. So I get x equals 1 or x equals negative 1/3. Okay, are those both answers? Let's look at the original question again. Find the values of C guaranteed by the mean value theorem. Well, the mean value theorem only guarantees values of C in the interior interval, right, between A and B. So this is critical. Exists a number C in that interval. Our interval is from -1 to 1. So does 1 work?
No.
Doesn't work. It's not on the interior interval. It's at an endpoint. Does negative 1/3 work? It does, right? So that's our answer. Okay? Makes sense? Okay. How about that guy? A little harder function. Okay. First of all, does it meet the criteria? Well, there's two parts to the criteria. Is the function continuous on the closed interval? So where's the only place where this function would not be defined, where it'd be discontinuous? Okay, so x can't equal 0. But that's okay, because that's out, it's not on my interval. So far, so good, right? Is it differentiable? Well, I don't know, we gotta take the derivative and see, right? So this is a quotient rule problem, so let's take the derivative. So, let's see, quotient rule, what do we got?
X minus
Okay, so low times, well, and what's the derivative of the top? 1, okay. Minus, good. Quantity x plus 1. And we wouldn't have to write the 1, the derivative, right, of the bottom is 1. All divided by. Okay, so what's that give us? X minus 1. Okay. So where is this function not differentiable? Also at 0, okay? So it's not differentiable at 0, but we already kind of knew that anyway, didn't we? Because think about all the places where functions aren't differentiable. They're not differentiable at sharp corners. You already pointed that out. But technically, when we talked about this at the beginning of the year, we said they're also not differentiable at gaps in the function, right? And so there's a place here where the function's not defined, and so that's a gap, has to be, right? There's at least a hole in the function there, right? So we already knew it's not differentiable there, but honestly, we don't even care, because we already disqualified the value 0. So really, the fact that it's not differentiable there is superfluous. We don't even need to know that, okay? But once again, that's not on our interval, so we're fine. So it does meet the criteria of the mean value theorem. So there is going to be a place where this is true, right? Where the slope of the tangent line is equal to the slope of the secant line connecting those points on the function, right? We already took the derivative, so we already did the calculus we need to do. So we just have to find the place then where the derivative function is equal to the slope of the secant line. So that's f of 2 minus f of 1/2 over 2 minus 1/2. So what's that give us? What's f of 2? There's our function. 3/2. Minus f of 1/2. On the top, I'm going to get what? 3/2 divided by 1/2. 3. Yeah. So 3/2 minus 3 divided by 2 minus 1/2. 3/2. Okay, so what's that going to give us then? That's on the top, we're going to get 3/2 minus 6/2. divided by 3/2?
-1.
-1. Okay, so we're just looking for the places where -1/x² equals -1. What if we just multiply each side by -1? Get rid of that. And then how do I solve this one? If 1/x² equals 1, yeah, what do you got that, but what if it were a little harder? How do we solve a ratio equation like this? Yeah, we could just cross multiply, couldn't we? And get, right? So we could cross multiply and get x² equals 1, or I could take the reciprocal of both sides and get x² equals 1. Either way, I get x² equals 1. What are my solutions to that? X equals ±1, but our interval only goes from 1/2 to 2, so what's the only one that we can keep? 1. Okay, so that's where it happens. Okay? How about a trig one? Okay, so let's, and it's worth talking about the trig stuff a little bit. Of course, we're not going to be as comfortable with the trig stuff as we are with the algebraic functions. It's always that way. So think about the trig then. Do we meet the criteria? Is the function continuous? And just think about the individual pieces, because there's an important point to make here. If I've got a function that's written as a sum of parts like this, I've got different terms in the function. All I've got to do, if I want to find the places where the function's discontinuous, I can just look at each little piece individually, and then if anything, like if I had something like, for example, let's say I had g of x equals 3x² plus 1/x. Well, what's the value of x where this function is undefined? 0, because there's my x on the bottom. The first term we didn't care about. That's the term that was important, right? Same thing here. So we've got 2 times sine x. Think about a sine function. Is sine discontinuous anywhere? No, it's fine. It just goes on forever, right? What about the sine of 2x? All that does is just compress the function a little bit, right? But it's still just a sine function, so we're fine. It's continuous everywhere. How about the derivative? Let's take the derivative. And I should probably add those implied parentheses, right? At least in my mind. So what's the derivative? Okay, derivative of sine is cosine. Now how about this one? Derivative of sine 2x. What's that going to be? It's just a chain rule, right? Derivative of sine hand is cosine hand, times derivative of hand is 2. So we'll put that out front. Okay, so is the derivative function okay everywhere? Yeah, same deal. Cosine instead of sine, big deal, right? So all we got to do then is do the algebra. We're going to set the derivative function equal to the slope of the secant line. Well, this time let's just figure that out as we go. So what's the value of the function at pi? What's sine of pi? 0. What's the sine of 2 pi? 0. So I'm going to get 0 minus, how about the sine of 0? 0. Sine of 2 times 0, so sine of 0 is still 0, right? So on the top I just get 0 minus 0. On the bottom I get pi minus 0. Well, 0 divided by pi is 0, right? So I'm just solving the equation then. Where does 2 cosine x plus 2 cosine 2x equals 0? What's one thing I could do right away to make this a little easier? Say it again? Divide by 2? Okay, I could divide both sides by 2, right? So now this now becomes a little tougher, right? Now this is one where this takes you back to the trig class a little bit, right? Now what's the problem with this equation? And I always think it's good to go through a couple examples like this throughout the year. What's the problem with that, with those two trig functions? Well, I got a 2x and an x, right? We got different angles. So I'm comparing apples and oranges here, right? if I want to solve this trig equation, when I'm solving a trig equation, what I want to first do is I want to be able to write it as a trig equation with the same angles in all the trig functions. Because that's really difficult to do. And now we're talking about, angles are growing at different rates. That doesn't work well algebraically. So I've got to use a trig identity. I've got to turn cosine 2x into a trig expression involving sines, cosines, whatever, trig functions of x. So do we remember those? Probably not. I would guess you probably don't.
You really think it's a double angle stuff?
It is. This is double angle stuff.
I think we tried.
So do you remember what sine 2x is?
2 cosine sine x.
Yeah. Okay, if you remember that, so these are a couple that it's just worth remembering. These are the ones, there aren't very many trig identities, you honestly think. I don't remember all of them, I really don't. There's just a handful of them I remember because you use them all the time. The other ones you just look up when you need them. This is one that's important to know. Okay, the other one, cosine 2x, there's 3 forms of it you might remember. There's only one you gotta remember, and the other 2 come for free if you remember the one form. It's this. Cosine squared x minus sine squared x. Those, it's just good to know. Okay? You just kind of know those. And you'll use them enough that you probably will remember them anyway. But this could be written in a couple different ways, because if we want to write it in terms of all cosines, for example, well, what's sine squared x? We got the big one, you always got to remember, the one we use constantly, is the Pythagorean trig identity, right? Remember that one. Sine squared x plus cosine squared x equals what? 1, exactly, right? So we use that all the time. So if I want to rewrite this in terms of only cosines, all I'd have to do is replace sine squared x with 1 minus cosine squared x, right? So we end up with cosine squared x minus sine squared is 1 minus cosine squared x. Well, if I just distribute the negative, doesn't that just give me cosine squared x minus 1 plus cosine squared x? Okay, so the other useful way we can write this is cosine 2x equals 2 cosine squared x minus 1. Do you need to remember it? Not really. That's one I just remember because I've used it so much, but if you remember this one, that's pretty easy to get, right? But what if we need to write it in terms of just sines? Just do the opposite, right? All we'd have to do there is say cosine squared x, which is what? If I solve for cosine squared, in terms of sine squared. If I solve that for cosine squared, what am I going to get? Say it louder.
1 minus sine.
1 minus sine squared, right? So here, this would just give us 1 minus sine squared x minus sine squared x. Isn't that just 1 minus 2 sine squared x, right? So those are the other useful forms. Which one are we going to want to take advantage of here? Yeah, I'd like to write this in terms of cosines, since I've already got a cosine term, right? So I get cosine x plus cosine 2x. I would just write as 1 minus, hold it, 2 cosine squared minus 1, that's right. Right? And that's all equal to 0. So what's that give us? Well, that gives us a trig equation, but I've got all cosines in it, and the angles are all x's. That's good, right? So I get 2 cosine squared x plus cosine x minus 1 equals 0. Okay, so that's good. We cleaned it up. So we got our trig equation in a form that makes sense. Same trig functions and same angles. what good does that do us? Now, remember that cosine squared x is really just the same thing as saying cosine x squared, right? Hold that thought.